So today is 7th May. So last time I sort of finished whatever I wanted to say about interaction between or of the two topics of special theory and EM, and how EM and special theory they both bond together, and how the action basically completed with how the full action of EM, including fields and charges, that was invariant uh, when you have this Lorentz transformation. So infinitesimal Lorentz transformation, and how you put it, do it on some local region, and your action is invariant. And so everything that comes out of that action, meaning the equations of motion of charges as well as the Maxwell's equation, those are invariant. So that was what we did. And so that was what where we completed. Uh, and Now what we're going to do is we're going to move on to the next major topic, which is radiation. So we are going to talk about radiation, and there are few different ways to think about this. Depends on the instructor. So for example, if Sushil, who is in DNAP, I mean, he has taught this course quite a few times. So when he teaches that, then he spends a lot of time in radiation. He talks about waveguides and that kind of stuff. I will do more radiation more from the theoretical perspective, in the sense I will do more from radiation which will be which finds use in particle physics, in astrophysics, stuff like that. Okay, but there is of course some basic things that needs to be done, and for that, yes, last day we started on having a small 5-minute recap of Green's function. So we looked at Green's function over here, and basically we showed that this Green's function is defined, saying that the Green's function is basically the solution of the point charge. If you find the potential, then that is the solution of the Green's function. And so the total potential is just if you integrate the Green's function over the charge distribution. Okay. So that was how the Green's function is introduced. So once we know Green's function, we can solve this kind of equation. Then we know Green's function, and then the potential over here, as you can see, is just an integral over the Green's function. Green's function being something that modulates the charge density. Okay. So it's the Green's function in the kernel. Now we did this because we are going to use Green's function in our lectures today. But before we do that, what I thought is that we're going to quickly do again a bit of recap of things that we have done, and some basic of radiation. So when I talk about radiation, of course, I mean energy transported away. That's what radiation is. So transported from the source to the field, somewhere which is not at the source. So this is basically, and the way it transports is basically due to electromagnetic waves. So waves, as we have showed before, the waves transport your energy, the wave packet transports energy, the wave packet transports momentum, and both move with the speed of light that we showed. So we're going to recap it again, once again. Look at the basic equations of EM waves. And then after that, we're going to go and see how we can talk about radiation when we know what the source is doing. So if there's a source has some charge and the charge is moving, and if this accelerated charge gives you some potential and there is some radiation far away, calculate how we can do that. That's what we're going to do after this. Okay, so but first let's start with some first 15-20 minutes, maybe a little more basic review of EM waves. First, very important, I will make my coffee. So, physics and coffee, or physicists and coffee are, two interchangeable terms. And there's a disaster in GTP that the coffee machine has broken down, which basically means everyone who drinks coffee just cannot go and so now all of us have to find alternate arrangements for coffees. Anyway, I don't know how many of you are coffee aficionados by now, but I can assure you, by the time you finish your PhD and go out, many of you will really, really hooked to coffee. So when I started my PhD, we didn't have coffee machines. There was no coffee, nothing like that. But by the time I finished, I was drinking coffee like guzzling it out. So let us start with some review of EM waves. Okay. And we'll start with the very simplest case of Maxwell's equation without any sources. Okay. So without sources. So we have so E is equal to 0. Curl of E is equal to minus 1 by C del V del T. And so now if I take the last two equations, then I can take the curl of E. So take this curl of E equation, take another curl of E. Okay. And then substitute whatever I get from the curl of B equation. So this last two equation use vector identities. You get basically the wave equation for E. So from these two equations, you can get the wave equation. The wave equation is E minus 1 by C squared del 2 del T2 E. So the similar equation holds for B. So similar equation for B. Because if I look at the Maxwell's equation over here, this Maxwell's equation is symmetric when E goes to B and B goes to minus E. Because equation symmetric. E going to B and B going to minus E. Okay. So now what we want to do is we want to find the solution to these equations. So the way is we consider solution, which is an exponential, so some kind of oscillation. Okay. So write it in the exponential form. So we'll write down my E and B as
Sir?
Yeah.
Sir, even if you do the even if you try to find the equation of B at first, and then you change it with E, then you also get the same equation. So then how the symmetry is reflected here? Because we need to then change B tending to minus E.
Huh? What? So you can take any of this equation and you'll get an equation for E and you get equation for B.
Yes, but
The same equation.
you have this last statement that you have said that Maxwell's equation is symmetric for E tending to B and B tending to minus E.
Is invariant is a better word.
And it's and you the first symbol that you have given, it means the above things happens because of it.
No, I didn't say the above thing happens because of it. I said there will be a similar equation for B. Because over here, I can write down the Maxwell's equation over here exactly in terms of just E and B. I can, because if I change E to B and I can change B to minus E, I'll get the same Maxwell's equation.
So if you start with the equation of B at first,
Yes,
and then if you change it with minus E, will you get the same, or if you change it with E, you will get the this equation?
you have to do both the, you have to change both the E and B. You cannot just change one. You cannot just change E to B without changing B to minus E. Both these things has to be changed. I mean, the Maxwell
Okay,
symmetry
I got
remains
it. Yeah.
when both the things has changed. One change is not enough. These two together gives you the symmetry. You think of the four Maxwell's,
Yes, yes.
if the 4 by
If new
4,
you can say.
yeah, you cannot just change one of them. So consider the solution. So let us do simple solutions. Consider solution of the form like this. So I'll have my E, okay. This will be, I will define very soon. Let me call it some A1 cap E0 e to the power I k dot R minus omega t. Okay. And so this k, when I write, these are all small k's. Okay, these are never, so these are never large, not capital K typically. So over here in my pencil, it's very not so easy to, I mean, quickly if I write it, it's not so easy to differentiate. And B will be very similar. So A2 cap B0 I omega t. Okay, so we have a solution for both E and B. Now over here, when I do over this A1 cap and A2 cap, these are unit vectors. Okay, E0, B0, these are complex numbers, or complex also but constant. Okay, my K vector is K times n cap. So this is the wave vector. N cap is the direction of propagation. Okay, so this is wave vector. So just doing it once for W is basically the frequency. N cap is direction of.
Sir,
Yes.
then electric field should be a real part of that, right?
Yes, we will come to that. Yes. At the end of it, you have to have something which is real. But over here, just wait. You'll see how it comes. Okay. Okay. So at present, this is like this. Then, so few things we can immediately say. Number one, that these waves are traveling in a direction which is n cap. Okay. So waves are traveling in n cap direction. Then what the next thing you can say is the surface of constant phase that advances in time. So which basically this first thing means surface of constant phase advances in time along n cap direction. Then what we can see is that if I want the full solution, then what we have to do is we have to superimpose. So if I superimpose solutions in all directions and all frequencies, so superimpose solution in all direction and all frequencies, then we get the most general solution. This gives the most general solution. Okay. So this is the most general solution for the source-free Maxwell's equation. So if I now substitute this into the Maxwell's equation, the first for Maxwell's equation, then, so if I substitute, I don't know, let me say, let me call this 2, let me call this 1, so substitute 2 in 1, then you will of course get 4 equations, which will give you the relations between this this A1, A2, K, all these things. So we'll get these 4 equations. So I want to go on to it, but maybe I will just write it down. So
Sir,
yes.
and the weightage of the different frequency, the solution of the different frequency will be decided from the initial condition and the boundary values.
So depending on your problem, you will have to. Again, just wait for 5 more minutes. We will come to this, how these different frequencies are. So it will depend on what is the, what kind of wave it is. It will depend on what is the pulse profile. It will depend on, so it will just depend on the problem, how you give the weightage on the different frequencies, how you got the average on the different time. Okay. That will completely depend on the problem, what problem you're basically tackling. But it is true what you are saying in a sense. It will all depend on, and this boundary values come as part of the problem. Okay. So all these things will be depending on the problem. This is a general thing that I'm saying right now. And after this, I will again generalize. I'm not going to go to specific problem, but I'm going to try to show you how you think of these frequencies, how you think of frequency intervals, time intervals, how to think of it when you think of these waves. I'll come to this in a moment. And all this about relation between real and complex, all these things will come. So let me go through 2-3 slides. Then you will have an idea of what I'm trying to lead to. Okay. So I substitute this, and things that I'm doing over here, we have actually done before in a slightly different formalism. You will see some these conclusions that I'm drawing over here. We have already drawn it when we talked about the speed of light. Remember, we talked about the speed of light in one of the lectures. Over there, the same conclusions were drawn in a slightly different way. Okay. So I have I, K, K cap. Did I write K cap or just a K? I write K. K dot 0, then I cap 0, I omega by C to cap 0, and then I also have I K cap cross 0 is minus I omega by C A1 cap. So you get this 4 things. Now, if you look at the top 2 equation solutions, so this one and this one. So what are the things that we come out of this? First of all, let me write this as, I should give numbers over here. 3, let me call this 4. So from 3, you see that A1 cap and A2 cap, these are transverse to K cap. So from 3, we get A1 cap and A2 cap. transverse to k cap. Okay, so it's basically transverse to n cap. So that's first thing. Then from the cross product of the two bottom two equations, okay, then you will see that A1 cap and A2 cap are perpendicular to each other. From 4, A1 cap is perpendicular to A2 cap. Okay. So therefore, the thing that we knew from beforehand, and also we did in that speed of light lecture, we have A1 cap, A2 cap, and K forms a right angle triad. Okay. So this is something that comes immediately as soon as we write the solution in terms of a traveling wave. Given the traveling wave solution, the Maxwell's equation immediately forces us with these constraints. Okay. Now, what about E0 and B0? So E0 and B0. So E0, if you look at it, will come out to be omega by Kc B0. And similarly, B0 comes out to be omega by Kc E0. So I can write down E0 as omega by Kc whole squared E0. And so this basically tells me that my omega squared is equal to K squared C squared. Now, you know that your omega and K are positive, right? Because that's how it goes. So W and K are positive because there's no negative frequencies, right? So this basically tells me my omega is equal to Kc. This immediately tells me then E0 is equal to B0. So now we have basically got everything about the solution, that we have a wave which is traveling, whose E and B, they are basically of the same magnitude at any point of time. Their directions are perpendicular to each other, and both of them are perpendicular to the direction of the traveling. Now the phase velocity, the wave sort of propagates the phase velocity. So you can calculate the wave propagates. Okay. With phase velocity. So your phase velocity V phase is omega by K, and that is C. So this is something that we found before, that the C was actually the velocity of the propagation of the energy, and C was also the velocity of propagation of the momentum. That was what we had done before, right? So this is, now if we are in vacuum, then the group velocity is also the same. So in vacuum, V group is d omega dk is also the same. But if it's not in vacuum, then this may not be the same. Okay, so because then your omega will depend on your k. So then d omega dk is not the same. Okay, so now that we have established the simplest thing about this EM wave, we can talk about the energy flux and the energy density in these waves. Okay, and so this of course comes in terms of the Poynting vector. Now when we talk about Poynting vector over here, because E and B, both of them are sinusoidal in nature, it doesn't make sense of talking about Poynting vector at one point of time. So we must talk about something which is a time average. So it makes sense to think about Poynting vectors, energy flux as a time average quantity. Okay. So we need to think of time averaging when calculating energy flux, that is Poynting vector and energy densities. So as a homework over here, you want to, sort of look at this. Suppose, so this is where this complex and your real thing comes out. Suppose I have two complex quantities. So let there be two complex quantities. Okay. So one is A and T, other is B and T. Okay. So these both have same sinusoidal time dependence. Okay. Now, E of T, I can write something like some complex quantity A, e to the power I omega t, and B of T I can write as something like B e to the power I omega t, something like this I can write. Then show if I take the average of AB, okay, this turns out to be half the real part of A, B star, okay, which is the same as half real part of A star.
Sir, for this, first of all, we need to take a real part in the definition of it.
Yeah, so I have shown you how it is over here. So A and B are, this full A is some complex where you can have this script A is a complex number, so you can take the conjugate of that.
But sir, if we directly take the average, it will come out to be 0. We can clearly see that.
No. What I mean by this is basically this. Real part of A and B, real part of okay. This is what I mean.
Yes, sir, then it's fine.
So show this is equal to this. This is just a
Okay.
shortcut of writing.
We have already done this in the assignment 1.
Yeah. Oh, I've already given you this homework, is it? Assignment. Oh, I see. It was there in the assignment already. Okay, good. Then I'm going to use it. I'm going to use this. I'm going to use it to define the time average of the Poynting vector. Okay. So I'm going to use this to get the time average of the Poynting vector. And this will be C by 8 pi part of E0 star. Okay. Similarly, you can write down the time average of the energy density. This will be C by 8 pi Square C by 8 by B0 square. Sorry, what I'm saying, this is S. This is S. Okay. Now we can write down the same for the energy density U. This will be 1 by 16 pi. So go back to your density. Real part of E0, E0 star plus B0, B0 star. And so this is 1 by 8 pi E0 squared, or is equal to 1 by 8 pi E0 squared. And so the thing that we got before in different ways, we have got it in different ways, that these ratios. So remember these ratios, we talked about the ratios of the Poynting vector and the energy density when we talked about, when we did it in the velocity of light. We talked about when we did it in this full Lagrangian, showing one of them had this kind of properties. So over here also basically tells me that if I do this, so the energy flow is also at the speed of light. So the over here, the energy flow in the wave is at the So now, given this, we can talk a little more about, when we talk about these waves and energy flows, we can talk a little more about the radiation spectrum. Okay, what do we mean by radiation spectrum? So these are things which is not immediately relevant to what will come in after this, but this will become relevant when we talk about individual processes, like for like Cherenkov radiation or synchrotron and things like that. We have time, we'll do those things in detail. So over there, to understand those things, we need to have an idea of what we mean by radiation spectrum and how do you want to tackle radiation spectrum. Okay. So I'm going to say a lot of things over here about radiation spectrum. But it will be very basic. So, the spectrum of radiation depends on the time variation of the electric and the magnetic field, right? And so the consequence is that it does not make any sense to talk about a spectrum at any instant of time. So first thing that I want to write is that wave means time variation of E and B. So, excuse me. So for spectrum doesn't mean to talk about E or B at an instant time. Okay. So spectrum basically means as a function of the frequency, right? So it doesn't mean to talk about this is the frequency at this instant of time, because anyway, your E and B are changing with time. So what we have to do is we have to talk about it valid only for some delta t. So we need to talk about radiation spectrum. Whenever we talk about radiation spectrum, it always means we talk about some interval of time, okay, some time interval. So if we have a record of the radiation, okay, then we can say that we can define the spectrum, okay, with some frequency interval in this time interval. So if we can say, if we have a record for some delta t, then we can define the spectrum for some delta frequency, because spectrum means I need to know the energy as a function of frequency. So within some frequency interval, I need to know the energy dependence of the frequency. But the thing that we must follow is that my delta omega times delta t must be greater than 1. Okay. So this is a property of the wave nature of light. This has not necessarily a property of the quantum nature, although you can derive this kind of uncertainty by assuming, energy time uncertainty principle and using your quantum theory. So this will give you a similar, except this one will have a different, will not be one. But even without quantum theory, just from this wave nature of light, if I want to get a sense of the spectrum, it means that if we have a very small knowledge of my delta t, then the reciprocal knowledge is less. So both of them cannot be. So if you have a larger delta t, then we have a much more precise idea of the frequency interval. So we can precisely look at the frequency. But if the delta t is small, then we cannot precisely look at the frequency. Now, we can think it in terms of energies also. So we can think of in terms of what is the energy per time, per frequency, so that kind of stuff. So if we want to do it like this, we again look at your E in terms of this traveling wave solution. Okay. So if you think of a finite pulse, so finite pulse basically means that your E of t must go to 0 as t goes to plus minus infinity. So take a finite pulse. So take a finite pulse. Okay. So E of t, which has a finite pulse. So basically it vanishes as t goes to plus minus infinity. Okay. And for simplicity from before, what we do is that so E of t is a finite pulse. So E of t is basically the same as so I define it like this. Then I can write down my E of frequency by doing a Fourier transform. So then this comes from E of t. So what I write down is E omega is equal to 1 by 2 pi So remember that over here, as your t goes to plus minus infinity, the UFT sort of falls down. Later, we will see how we can use this kind of pulse definition, but still apply it to much, much longer trains by taking a different kind of averaging. Okay. So this is also related. So my E of t is also related to my Fourier transform of E of t. So this basically goes from Yeah. Yep. Now my E hat omega is complex. Okay. However, since E of t is real, since E of t is real, one can show what we can show, and these are things that you can do it very quickly, that my omega is equal to omega. So this basically means all the negative frequencies are eliminated. So there are no negative frequencies. Okay. So frequencies
Sir,
Yeah.
sir, sir, in the first part of of today's lecture, you have told that E0 is a complex thing. So, sir, how ET can be real?
No.
Even
So this is exactly what Nikhil was asking, right? At the end
yes,
of
yes.
it, you're talking about something which is observable. So E of t over here, the full thing is the real part of this. So when you think over here, when we use this average quantities over here, it all came as real of A and real of B. So when we talk
So, sir,
about the wave, we talk about the real pulse. It is a real pulse. So we use the real part of this, but in general, when we write down the general solution, we start with a complex, but then when we applied it to physical cases, we'll have to use our physical priors and take out the real part of it.
okay, sir.
So see, because E of t is actually real, because I can measure the electric field at some point of time, right? And that tells you, because of that, it tells you that your frequencies, which is also something that you should expect, like your frequencies cannot be negative, right? Frequency is how many times it is
Yes, sir.
happening. It cannot go negative. So that makes sense. If it was not real, if E of t was not real, if you're taken with the complex, then of course there was nothing to do with, there is no constraint on your frequencies. Now, given this, we can write down the pointing vector in terms of energy per unit time per unit area. So pointing vector is the flux. Okay. So your pointing vector okay, is energy per time per unit area. That is your pointing vector. So this is W. So W is sometimes, so one of the things I have to tell you, and this I faced last time also, sometimes I write energy as W, which is very common in electromagnetic books. Some books will use W. Sometimes I write energy as E, but I will make sure when I say E or W. I mean, okay. Because sometimes E is also your electric field E. So over here it makes sense to write it in W, not to write it in energy, not write it as DE. So per unit time, per unit area, that is 4 pi by 6. See, this is consistent with this over here, because this was the average. Okay. Whereas over here, I have not done any averaging over here right now. So this half term is missing. Okay. So now this is the energy per unit time per unit area. I can write it down in the total. So you can integrate this. Okay. So if I integrate, then dw dA will be c by 4 pi square t dt. Now what we can do is that we can use Parseval's theorem. When I use Parseval's theorem, then I can equate this thing, this integral p square t dt over the total interval. I can equate it to an integral of d omega, which is the integral of the frequency. So if I use Parseval's theorem, then what I have is that this integral e squared t dt minus infinity to infinity. This is basically, I can write down as this basically came from the way these two Fourier transforms were defined. Okay. So the power spectrum over here and on the right hand side, they basically agree with each other. Now, remember this E of omega has this symmetry, right? So I can use this E of omega symmetry. So use the symmetry for E of omega. So that is basically, remember, because omega going to minus omega, it was symmetric. So I can write down E squared. And this is the same as, I should put in a hat over here. Okay. So when I do this, then I can simplify over here. And so then I can simplify using this. So I can put it in the previous equation. And then I can simplify. And then this 2 pi will become a 4 pi. And then what will happen is that I'll get, sorry, I'm getting this all the time. I can get the energy per unit area. Now, instead of an integral over t, I can get as an integral over omega, except that there is this 4 pi is gone. This 4 pi, this 2 pi will become 2 pi, will become 4 pi, and that 4 pi will cancel with the previous 4 pi. So this will be gone. So this will just be a c times 0 to infinity. So if I have an equation like this, then I can identify, because this is an integral over d omega, I can identify, so from this equation, I can identify what is, so from this above equation, I can define so remember previously we started with energy per time per area. Now, given this last equation, I can write down energy per frequency per area. Because this was an integral of a frequency, this is how I can define it. This is nothing but C times okay. This is what it is. So this is the total energy per area per frequency range in the entire pulse. Okay. So this is very important, is one word over here. Total energy per area per frequency in the entire pulse. The entire pulse is very important over here. And it's an entire pulse because it started when we integrated the time from minus infinity to plus infinity. From there itself we came over here. Okay. So we have not written per unit time. So it's over the entire pulse. In fact, we cannot write per unit frequency or per unit time at the same way. Okay. So it can be either per unit frequency or it can be either per unit time. However, if this pulse, so this is an entire pulse, but if this pulse keeps on repeating, classic example is a sine wave. So we have a pulse, it just repeats. Okay. Then we can try to have an average time scale. Then we can slightly remodel this, and which comes very, very handy later. We can put in an average time scale. So if the pulse is repeating, then we can introduce an average time scale. Okay. So then we can put in a t in this equation. So then what we can do is that we can write it down like this. Then we can write down d omega dA dt. But this is the definition where this dt comes through this average time scale, which is okay. So this is nothing but c by t . We can go a little more farther. What we can do is that if it is really, really long, okay, so if this property is, does not change at all with time, so classic example is a sine curve. It can go on for infinity, is the same thing. In that case, we can actually take a very large time period, okay, and then this e squared omega, that will be defined within that very large time period. Now, this equation will turn out to be a very, very important equation. The structure of building this equation was very simple, but this equation will turn out to be a very, very important equation later in this radiation theory. Okay, where a lot of times we will always define things within a time. So we'll try to basically get some idea of this T, suitably define a T, and try to think of radiation averaged over that time period. So for example, to give you a hint of things that will come later, if we have time, is suppose, let's say, you know that accelerated charge radiates, right? So if I'm having a cyclotron or something, and an electron is going down and down very fast, it will radiate. That's something that you know already. You also know that if it's relativistic, then the radiation is in a cone. Okay. Now, if I want to study this kind of radiation, so what will happen is there's a pulse will come. Because as soon as the cone goes outside your eye, you cannot see that. So when a cone comes in your eye, you see a pulse. Right? So that's very simple to understand. If I want to calculate this kind of properties over there, then you see there are two time scales over there. One time scale is the time scale in which this electron is moving. That is one time scale that gives you some frequency. And typically, for non-relativistic cases, the frequency of the light or the pulse, the energy, that is basically related to this frequency. And we'll do this in great detail later. However, if it moves very fast and you have this beaming effect, then there is another time scale that is entering. That time scale is when this beamed thing that is coming to you, okay, is facing you. So I can think of some time scale, which is a different tau, which is the time, just the time in which the beam is facing you, or slightly more than that time. Okay. So now we have two time scales. And this will basically give us an opportunity to write things, simplify things by decomposing solutions into, we'll see, the solutions will become very complicated, but a lot of things simplification will happen. We can decompose solutions into two timescale regime. One, which is the timescale, one timescale, which was the timescale, physical timescale in which it is moving, and the other timescale is a much shorter timescale, which will be basically depending on when the beam is facing you or the beam is away from you. So this average time scale for repeating pulses is a very important concept, and we are going to use this again and again. Okay.
Sir,
Yes.
sir, but most of the medium consist of some kind of damping factors. So, how much it realistic to apply this concept in those materials? Because there the pulse shape or the function of pulse is not repeating at all. It will
Yes.
decay.
Right. So let me show you what happens to your damping. So let me show you. I knew this kind of thing because I have drawn three pulses. Okay. One of them is a damping. So let us try to see the properties of these pulses. Okay. So E of t will vary with time, and then there is some spectrum. And remember, your total this pulse will have a delta, your delta omega will depend on this, because delta omega delta t was 1. So now I have basically fixed my delta t being some average time scale. So delta omega will be like this. So let me draw some pulses, including one with damping, and try to see what we find in the time domain, what we find in the frequency domain. Can we do this? Later we will do it calculations explicitly, but now I'm just going to give you an example. So suppose I have a pulse, which is basically something like this. Okay, so this is t, and this thing is basically E of t. Okay, and I can think of the half width approximately as the average time in which I'm going to look at this. So I can think of this t over here. Okay, so for one, I've talked about a delta t. The delta t over here is basically the half width. Okay, the delta t is the capital T, which is the half width. Okay, and in this case, I can find the spectrum. So this was E of t. The spectrum will be E omega, right? I can find the spectrum. Spectrum will be, and the spectrum will be something like this. So so over here, this has a delta omega, just like delta t. So delta t is equal to t over here. This is the spectrum. So spectrum is C squared is the spectrum. And this is basically 1 by t. So if this pulse was very, very thin, then over here it will be, a lot in the frequency domain. But remember, over here, only this part of the spectrum. Okay. Only this part is valid. Okay. So this is relevant, because just for the sake of showing the symmetry I have drawn it over there. So this is the relevant part on the right hand side. This part is now when it's just one pulse, this is like this. I can choose the delta, the t to be just the half width. Over here, this is the most reasonable time period to think of, or over which I want to look at. Okay, delta t. Now, suppose my pulse was different. My pulse was this. Okay. So you will bad drawing, but anyway. So this is a sine wave. Okay. So I have a sine wave pulse. Okay. Again, so this is u of t, this is t. Now over here, I would like to look at this t, and as I said, by using this average t, I can extend the region over which I want to record this pulse. So now my t over which I'm going to average, that's a large value, t like this, over which this pulse repeats many, many times. And then, and this et was basically sine, let's say, sine omega naught t. That was the frequency. Then in the frequency domain, what I will have is that C again. Good. I have to find where is omega naught over here. And because this is so wide, the T is so wide, this will just be a peak over here with some side lobes. So the side lobes will be there. And so this over here, this is the width. This is the width. And this delta omega is basically 1 by t. This is how you will find the pulse over here too. So this is the power spectrum of the pulse. This is
Yes. It would be right to say that in the sine wave case, the all part of the spectrum are equally weighted. So we can take a large width for the large time scale for this. But in the case of a decaying wave function, where the energy contribution coming at maximum rate, that is within the half width full width half maxima, we would take that as a time range to average the things.
right. Now let us talk about slightly more where you see the decay. The first one was a simple pulse, simple decay. Second was one which went on for a long time. There was no decay. You can think of something which goes on for a long time, but still there is a decay, right? Which is the most common of the pulses, actually. I mean, this pulse, which is constantly maintained, is not very common. It's very difficult. This pulse is common, but again, this happens only in few cases. It's not common in the sense like you can find this kind of just one peak coming. Okay. Most common is something like this. So this was omega. Hold on. Where we have a pulse which goes on for a long time, but it also decays. So like this. Okay. So it has some kind of a this is E of t. Over here also, it doesn't make sense to have a t which is just half width of one peak. You want a t which is sufficiently large, okay? Just like the previous. You want to capture a number of pulses. So the larger the t, your better is your approximation, better is your calculation. So you have a t which is like this, let's say, okay. So let's say this is the t. And in this case, what will happen is so this, remember, again has sine omega t, okay. But then there is an exponential e to the power minus t by t. So this is what you in some sense said right now, okay, although you didn't mean it over here, that your t is such which sort of encaptures the exponential decay of the thing. So t gives you an exponential time scale of the decay over here. That's how I've taken the t. Okay. And then over here, what will happen is that again, it will be at omega naught, but because of this decay, what will happen is something like this. Okay. So see what I'm saying. Okay. So this is again your delta omega. The delta omega again is 1 by t. But now, as you can see, because of the decay, you do not have side lobes. See over here, the previous one, there were side lobes, they were ringing. This ringing has been erased. So depending on what your, so the important part over here is it is upon you how you take your t. So if you are, so it's a judgment. So over here, of course, is theory. Suppose we're doing an experiment. Suppose you're doing something. They were here, you have to take a judgment call. For example, if my judgment call told me that I will not take the t to be over here, I will average it out by some, let's say some t prime, which was, let's say, t by 100. So your t prime will be like this. Then you will not find, you will make a mistake of the Poisson spectrum. The Poisson spectrum will not come out to be right. So this case, for the Poisson spectrum to come out to be right, you must have a time period which is at least as large as the decay time scale of the system. If it's less than the decay time scale of the system, then you don't get it. So this is a judgment that you have to, in your calculation, you have to make a judgment. What is the t that I want to take? Should I take a t which is something that comes from the system? So you take a something different, because your spectrum, your Poisson spectrum will depend on this judgment. Okay, so that's all that I wanted to say about pulses and simple radiation spectrum and stuff. Remember, we will go in great detail about the radiation spectrum later when we do specific cases. Okay, those will be mathematical. This gives an intuitive feeling of how things are. We should, I thought I would do a little more. I'm already getting this past 5:30 actually, but I wanted to do a little more. So if you would allow me, I will do a little more of this. Is it okay with you?
No, sir, there is a class at 4:45 after 5 minutes.
You have a class after 5 minutes. Okay, then we'll do it the next day. This I thought I would do very quickly, but it took a long time actually. I don't know why it took so much of a time. I had thought that I would finish it in like, half an hour, 40 minutes, and then I'll go to the next one. But anyway, this is an important, simple but important thing to understand. So next time what I'm going to go is going to go back to more mathematics. So we did Green's function, remember? We are going back to Green's function. But now we are going to do Green's function, which will be a slightly more generalization of the Green's function that we did before. So what you have done, it was Green's function in 3 dimensions, because when you're doing this electrostatic case to solve boundary value problems. We are going to now go to Green's function to talk about radiation. Radiation, of course, has time. Okay. So now we are going to generalize our Green's function into 4 dimensions. So it will be our Green's function, which will have both space and time in it. And we're going to show that we can use this Green's function technique to solve wave equations. The solution of wave equations using Green's function. That's what we're going to next do. So we'll solve the wave equations. Wave due to some charges, so we'll not get rid of the charges which we didn't do today. Today our Maxwell's equations were without any sources, but over there will be sources. So let's say there are some sources, we have some radiation, we have some wave. We're going to solve the equations using Green's function technique. And to do that, we are going to use gauges. So I'm going to talk about, so last day I did mention that we're going to talk about Coulomb gauge and Lorentz gauge and stuff like that. We'll talk about both Coulomb gauge and Lorentz gauge, and then we're going to solve things in the Lorentz gauge. Okay, so if you want to go ahead, you can look up Jackson. It's given in Jackson in great detail. Slightly complicated also. Jackson they make things unnecessarily complicated, but hopefully when I do it, you will be able to follow it easily. Okay, so that's what we're going to do next day. And after that, we'll go back to radiation and pulses and stuff like that, which will basically involve the solutions that we do the next time. Since you have classes today, I'll stop over here. And we'll do it on next Wednesday.